I don't know if we get the lights down a bit, especially on the front here. Well, I'm going to start off with a thank you and then a confession. The thank you is to Richard Clegg and to Tim Slingsby, and also to the whole team, Natalie, Steph and others, for the invitation and for organising this conference. The confession is that I am quite anxious about this talk. I'm used to giving a research talk, but this audience, I wasn't sure about how to pitch it, about the level, because I know there's some hardcore scientist engineers here. We've had talks on health and safety, educationalists, and obviously some more general non-scientists. So I asked Richard, what should I talk about? And he said, about 30 minutes. So for the next 29 minutes, I'm going to give you a flavour. So for this 3D image, in fact, stupid me, I didn't get glasses myself. No, you can't do that. Anybody at the front there? Yeah, I'll take glasses. So if you look at this image, it's for the best effect, it's, as in politics, red is on the left and where my heart is. If you stare at that, and for the best effect, if you move your head side to side, and even if that doesn't work, it makes me smile just from this angle. So that is a structure I'm going to come back to later on, but it's a very familiar crystal structure, and it's something to do with what Asa said about chemistry in the kitchen. So I'm going to give you a flavour of my work, and as with any flavour, I'm going to talk about, let's first talk about the menu of the talk. I'm going to start off with the starter, as you do, a brief starter on the energy challenge, and then the second is another starter, briefly talking about solid materials and where my area of research, materials chemistry, fits in to the energy challenge. The main course is to do with lithium-ion batteries, and then for dessert, a bit of Faraday links. In fact, it's a real privilege. I didn't realise as I walked in there would be a statue of Michael Faraday outside, and also there's a painting of Michael Faraday right here. As we know, lithium batteries have revolutionised those portable electronics, and in true theatre and cinema style, hopefully you've turned yours off. So let me start off with the energy challenge. I think it's well established that in the 21st century, this is one of the biggest challenges that we have, producing clean, sustainable energy. It's a very hot topic, both literally and metaphorically. And the literally bit, that the hot topic is that we're producing too much CO2, which is leading to global warming and potential climate change. And the problem with climate change is that it adversely affects, in particular, the poorest people in the poorest countries. I'm not going to go into the science of climate change. I'm not a climate scientist, but I think one of the best Q&A, question and answer reports out there is produced by the UK National Academy of Sciences, the Royal Society, and the US National Academy of Sciences. It's free on the Royal Society website. So if you want a really succinct report on climate change, I'd go there, and you can argue with Lord Lawson at your leisure. So what's going to happen in the future? We know there's going to be a mix. Fossil fuels will be still part of that mix. There'll be nuclear, and there'll be other renewable sources. There'll be solar on the left, wind, energy storage, well, I'll be talking about batteries, wave and wind, and obviously we can do our bit by conserving energy. Energy storage is arguably more important now than any time in human history. And one of the most successful energy storage devices is the humble battery. If you think about your daily life without a battery, it'd be very difficult. So, as I said before, it revolutionised those portable electronics. But what's the next challenges? Well, the next one is the electrification of transport, which I'll come on to later on. But the other one is grid storage, electricity grid storage. If we have a larger amount of renewables, wind and solar, so when the wind isn't blowing and the sun isn't shining, we do need energy storage. Batteries may be one of the technologies. There are other technologies for energy storage, large scale, pumped hydro, for example, but batteries will possibly feature. But what's critical, and this is probably the philosophy behind my scientific research and my scientific philosophy, is for breakthroughs, we do need new materials, we need some new science, new concepts, but also a greater fundamental understanding. So what are the questions I want to address for this talk? So for the next, I suppose, 25 minutes, what do materials look like on the atomic scale, hence the 3D glasses? For those not in the chemistry or science area, how do mobile phones work? How do ions, lithium ions, move within that mobile phone? And in the context of the theme of this conference, what about the next generation of lithium batteries? Can they be safer? And the last one, probably the most controversial topic, is was Shakespeare a chemist? So I'm going to answer those questions. So the first one is crystal gazing. So in terms of chemistry in the kitchen, this is probably one of the best examples. So this is just salt. So the stuff you sprinkle on your chips, on your pasta, and in my case, before a tequila shot. This is sodium chloride. This is salt. So back on with your 3D glasses for your first 3D. So this was the title slide. This was right at the beginning. This is sodium chloride. The large ions, or the large spheres, are chloride. The small spheres are sodium. And they form a very regular crystalline structure. That may seem obvious, but I want to get across that. These are very crystalline materials. Probably the best example of a non-crystalline material is glass, an amorphous material. It has no long-range structure. This has long-range structures. That's just part of the crystal structure. But an important aspect, keep your glasses on, an important aspect of solids is the fact that some of the ions, you may not know it, but some of the ions, very few, some of the ions can actually move. So have a stare. I don't know if this will work. I've tried this. Ooh, yes, thank you. Give me an ooh, yes. So that's ions moving. So that's very important. I find that so mesmerizing. I'm going to do that again. So these are ions, in this case sodium ions, moving through a crystal lattice. And that structure is adopted by something called silver chloride. If you replace sodium by silver, you get silver chloride. And silver chloride is one of the best examples of ions moving through a crystal. Does anybody know what silver chloride was used for? It was used for photography. And for young people in the audience, photography, we used to use this photographic film. We used to stick it into a camera, take it to Boots, and used to get 36 or 24 developed. I know that because I used to work for Eastman Kodak in New York. I used to get free film. But the dirty word you don't mention amongst Kodak employees is the word digital. So digital has killed off Kodak and Fuji. But silver chloride is a good example of ions moving. But let me move on to the godfather of ion conductors. And the godfather is Michael Faraday, one of my scientific heroes. Not only was he one of the preeminent scientists of his day, but he came from very humble beginnings. And he rose to be one of the greatest scientists the world has ever seen. So this is the back of the old £20 note. And you can see on the left him giving a lecture. And he founded the Royal Institution Christmas Lectures and in 1825. And that's probably he's probably giving one of his lectures, possibly on the chemistry of the candle. But anyway, if he had Twitter at that day, if he had social media, he wrote in his diary in 1835 that materials, when sought for, will conduct electricity in the solid state. So he was the first one to observe, experimentally observe, that some solids showed ion conduction. It was known that liquids conduct ions, but not solids, and he observed that from a fundamental point of view. So another aspect of solids is that they tend to be impure. So these are dirty crystals. So these beautiful gemstones have impurities in them. Obviously, when you deliberately add impurities, it's called doping, what I call the Lance Armstrong effect. So that deliberate doping will cause a performance enhancement. And here, the performance enhancement is just the beautiful colours. But another example of impurities is the crystal meth. Yes, that's a good example. In fact, the stuff I make is clear, as it should be. But But this leads on to the controversy I mentioned, and that's to do with Shakespeare. In Midsummer Night's Dream, and I know this because my daughter's doing her GCSEs, when Demetrius wakes up to see Helena for the first time, he utters these words. He says, "To what shall I compare thine eye? Crystal is muddy." What Shakespeare's trying to say here is that compared to Helena's beautiful eyes, crystals contain ionic impurities. So you heard it from me first. Shakespeare was probably a solid-state chemist. So computer modelling. So when I go to parties or dinner parties and they ask me what I do, rather than say I'm a chemist, because that usually means that they've walk away, I sometimes say I model. But instead of obviously modelling down the catwalk, I do modelling on the computer. And one of the best examples of modelling or model building is this iconic photo of Watson and Crick back in Cambridge in 1953. And from retort stands and clamps, they built up the molecule of life. And they, using data from Rosalind Franklin, her X-ray data, they worked out that the molecule of life was a double helix, whereas Linus Pauling and others believed it's a single or triple helix, and they eventually got the Nobel Prize in 1962. But that model building you can do now in seconds on a modern supercomputer. You can build up. This illustrates two things. One, I think science can be very beautiful. It's very much curiosity-driven, and you don't know where applications will form, because they were just working out that DNA was a double helix. But it's led to the fact that the whole chemical biology, biotechnology relies on that structure, the fact that it can replicate. So what are the modelling aims? I mentioned this because some people say, oh, computer modelling, just use a bit of software. So the three main aims in my view. One, it helps to assist experimental data. So experimental data, for example, in my field will be diffraction data, structural data, trying to interpret that. The second aim, can you use modelling as an atomic scale probe in itself? Can you actually get into a crystal and try and understand a bit more about that crystal that the experiments can't probe? Hopefully I'll show you an example of ion conduction. And lastly, can it be used as a predictive tool and screening? Very much used in the pharmaceutical sector to screen lots and lots of compounds. So the first, I suppose the main course, was to do with lithium-ion battery. And I mentioned that they have helped the portable revolution. So this is a photo of my old iPod and my taste in 1980s jingly-jangly guitar music, the Smiths. But what shows that, as in life, size is important. And here, it's the energy density of that battery is crucial. The energy density stored in a small volume and a small mass allows us to miniaturize our phone. In fact, phones could get smaller, but now phones have become supercomputers. So it's not just about making phone calls, it's about all the other stuff that goes with it. And that's why they're very, very power hungry. We would love a phone to be charged and last a whole year. But they're very successful. Over 3 billion cells are sold a year. And I remind myself the words basic chemistry, just to remind me to say that a lot of the early discoveries would not have happened without fundamental blue skies, curiosity-driven research. You can't always predict applications. In fact, it took John Goodenough at Oxford, who I think should get a Nobel Prize. He discovered it in Oxford in the early 80s. It got commercialized by Sony about 10 or 12 years later. So you can never predict how long it will take. So this shows, I thought I'd show one piece of data. This shows in a plot of why lithium-ion batteries are so successful. Up on the y-axis, up on the vertical axis, is the gravimetric energy density, how much energy you can store in a unit mass. And along the x-axis, along the horizontal axis, it's the volumetric energy density, how much you can store in a unit volume. And obviously, you want to get to the furthest on the right-hand corner, so lighter and smaller. So lithium-ion batteries fulfill those criteria. They've got still a long way to go in terms of how far you can go in an electric vehicle, but compared to lead acid, nickel cadmium, nickel metal hydride, they have a much higher energy density. So the next challenge I mentioned was electric vehicles, and already they're being used. The Toyota Prius, I think over 6 million have been sold, the Tesla and the BMW i3. But every car manufacturer is developing some form of electric or hybrid electric vehicle. I'm not a car engineer, but I show this, not because I'm into Top Gear, but I love this schematic of electric car for one simple reason. This label at the top, battery recharge plug not to scale. It's this massive plug, you know, you're going to drive around with. That's going to add to your energy density. So a couple of other things that you should take home with you. 30% of CO2 emissions in the developed world comes from road transport. And the problem with that figure is predicted, unfortunately, to grow because of rapid growth in China, India, and Brazil. And not surprising, they want to have what we have. They want to have cars as well. But that leads to a large amount of CO2 emissions. But also a big topic in the last couple of years leads to problems with air quality in terms of pollution. Just have to look at some of the pictures of Beijing and Shanghai. Another interesting statistic, and this is I always use because people are worried about something called range anxiety, how far your electric car will actually go. Well, did you know 90% of UK car journeys are less than 30 miles? Supermarket, the school run, even the daily commute often are actually much less than 30 miles. I had to show this for Richard's benefit. I found this on the web. So it isn't just about road transport. There's a growing research area on electric marine and actually a World Expo 2080, I don't know which number it's up to. And up there is another painting, just by coincidence, is Ampere. And there is an all-electric car ferry in Norway, in the fjords of Norway, called Ampere. And so that there are developments in the marine sector as well. So let me go back into my research. So if you ask me what is inside a lithium-ion battery, I'd say that's a very good question. And so view it as an electrochemical sandwich. So as any sandwich, you've got two bread slices. The bread slice on the left is the positive electrode, lithium cobalt oxide. So it's a cobalt oxide electrode. On the right is cheap and cheerful graphite, and that is the negative electrode. And in between, the meat, or cheese if you're vegetarian, is a very good ion conductor. It allows lithium ions to shuttle between the two. The problem with that lithium-ion conductor is that it's a liquid, it's a lithium salt in organic solvents, highly flammable. So how does it work? So when you plug in your phone tonight, just imagine that actually you're seeing chemistry in action. Lithium ions are going from the cobalt oxide to the graphite, and that's what that green symbol indicates, that you've actually just shuttled lithium ions. And what's shuttling is the electrons from your mains is helping that process. On the other side, when you actually use your phone, you're discharging, and the lithium ions are going that way, releasing an electron and powering your device. And that happens over and over again. So there is degradation over time, because you are essentially doing that nearly every day. And that obviously eventually leads to some degree of degradation. So you always wonder, why isn't my phone as charged as well when I first bought it? It's really because you are doing a lot of that process over and over again, thousands of times. But there is a problem. I mentioned the cobalt oxide. Cobalt is both toxic and expensive. So in terms of safety and expense, we're trying to move away from cobalt. So there is a lot of research replacing cobalt with other more benign metals. Before that, I'm going to show some more 3D images, but before that, for the non-chemists out there, these are two types of coordination around a metal ion. So the metal ion is in blue, and for those keen followers of solid-state chemistry will know that the oxygens are in red. And another way of representing that coordination is an octahedron and a pyramid-type structure, a tetrahedron. And that will become apparent why I've done that for the next one. So if you put on, if you put on your 3D glasses, these are the last of the 3D images, I think. So this shows an image of something in your pocket or your handbag right now. This material is in your mobile phone. This is lithium cobalt oxide, and the lithium ions are the spheres, and the sheets or layers are the cobalt oxide, you can see, and they're edge-sharing octahedra, the coordination I showed you before. So you can imagine the lithium ions, as you're charging, the lithium ions coming in and out between the layers or between the sheets. So, as in life, the important stuff is happening between the sheets. Sorry. As I mentioned, so Elon Musk's cars and the BMW i3, they're not using the pure cobalt oxide, they're replacing cobalt with a bit of nickel, a bit of manganese, but they have to keep a bit of cobalt in there to work effectively. So there's a lot of research on that. But can we move away from those elements altogether? And the simple answer is yes, we can. And this is an iron-based. Obviously, do a bit of shaking your head a bit. Even if you're not a structural chemist or a chemist of any sort, you can see straight away that that structure is very different from the one I've shown you before. This is a beautiful olivine structure. Olivine is a naturally occurring mineral, often close to volcanic sites. And here, I should do Attenborough, here there's iron oxide, it was his birthday recently, iron oxide octahedra, FeO6, and they're connecting at their corners by phosphate tetrahedra, producing this beautiful, elegant network structure. I've highlighted the lithium ions in yellow, and like I suppose, tube trains, they're actually forming a tunnel. So they are coming down that tunnel. And I call it the X factor of materials. It's non-toxic, it's cheaper, and it's much safer because you've got stronger phosphate bonds in this material. And this is probably one of the most studied of lithium battery materials in the last decade. And the last one of the structures, although not the last of the 3D images, this is something I've been working on the last couple of years. Can you make a battery from rust and sand? So we're looking at some iron silicates. Again, the lithium ions are the spheres. The iron are in the tetrahedra, and the silicate are in the tetrahedra. And again, a beautiful sort of structure and naturally occurring. So we're looking at using very benign materials and low-cost materials, and that's one of our research areas. Keep your 3D glasses on. This is a 3D image. I work very much in a consortium. As all scientists, we collaborate. And I collaborate with an engineering team up at the University of Strathclyde in Glasgow. And you may not believe it, but that is our test vehicle. That beautiful bond-like AC Cobra is our test vehicle. We test batteries, supercapacitors, and fuel cells in that around the streets of Glasgow. And as you can see from what they're wearing, it was a relatively warm day in Glasgow that day. And this is the last image, nothing to do with my research, but I thought it would be a wake-up call. This is a fantastic, move your head about. Those antennae, they just, they follow you around. It's a bit creepy. So that's a antennae. So if you're not into creepy crawlies, I apologize. So that is the last of the, and that's the wake-up call. So if, often after lunch, you kind of doze off. Right, so about lithium ion. I mentioned one of my questions, how do lithium ions move? And this is an image of the lithium cobalt oxide, and I don't know if it's going to come out, but let's try it out. So the reds are oxygens again, the blues are cobalt, and the greens, the very faint greens, are lithium. And what you can see, this is a computer model of the animation. This is the kind of animation that we produce from our simulations. We try and understand how lithium ions move. Lithium is number 3 in the periodic table. So it's the third lightest element, and it's the third smallest. So it's a tiny ion to see by experiment. So using computer modeling, we can actually begin to understand how lithium ions move through the crystalline materials when you're charging your phone. In this case, they're staying within the 2D layers. They don't actually go above the 2D layer. They just stay within that 2D layer. And then the other material I mentioned, the lithium iron phosphate, this is a slice through the structure. The yellow is the iron octahedra, the blues are the phosphate. This is very different. It doesn't work in 2D at all. This is a 1D conductor. So this was a clear prediction. We predicted that these conduct by a 1D channel. Again, like a tube train. And the problem with tube trains, they can get blocked. And that's the problem with this material. The ion conduction can get blocked. But you just need one defect or impurity in those channels along that 1D path. That was a clear prediction. I never thought that prediction would be confirmed. But some beautiful, elegant work by a team at Tokyo, headed by Yamada, they found from their careful neutron diffraction experiments, they could map out how lithium ions were moving. And they confirmed, not only was it a 1D conductor, but it went along that curved pathway, that sinusoidal curved pathway. So that was quite a nice confirmation of our modelling prediction. So what's new? And considering the billions of cells being sold, and this is where risk comes into it, and actually I suppose, lithium batteries are a victim of their own success. Now, whenever there's a fire, there's somebody with a mobile phone or something there to record it and go straight onto social media. So the events of a fire or even a Dreamliner fire are very, very rare, but obviously you want to minimize that risk. So I mentioned that the conventional battery is a liquid electrolyte. So it's a flammable organic solvent. So can we replace that with something safer? And oh yes, so that's just obviously a typical news item from The Guardian on the Boeing Dreamliner flammable. You can replace that liquid electrolyte by a solid electrolyte. But there are issues and challenges. Solid, just intrinsically, does not conduct as fast as a liquid. So obviously there's a challenge to try and up the conductivity within a solid. But there are advantages in a solid, as I said, safety. But the other advantage is that you can now begin to use lithium metal as one of your electrodes. At the moment it's graphite. Graphite is very effective, it's cheap, but lithium metal will be ideal. You could really increase the lithium energy density and get over that range anxiety that's probably overdone anyway. So that is where research, so there's an incredible amount of research, including our own, to look at new materials and new science in trying to develop new, safer solid-state batteries. So watch this space. You're going to hear more about this from people like Dyson and Elon Musk and others, but also on the academic level, the fundamental level. So this leads on to what's happening in the UK right now. I think it's quite an exciting initiative. This is on the back of the UK government industrial strategy, and very much pushed by one of the speakers this afternoon, Professor Sir Mark Walpott, when he was the UK science advisor. And the Faraday Challenge, in a nutshell, is the development and manufacture of batteries for the electrification of vehicles. It's only just started, in the last couple of months. And the Faraday Institution is actually being opened right now. I'm missing the opening to be here. It's a virtual centre. It's really an amalgamation of university research, but there is a HQ at Harwell being opened today. And the four main projects that are being started straight away with industry: degradation and battery life, solid-state batteries, multi-scale modelling, recycling and reuse. It's just started, but I think it could be a really exciting development for UK PLC and UK manufacturing, because what we don't have in the UK is really a manufacturing base of batteries. We do have a very, very vibrant auto industry. It's one of the biggest employers in the country, but we don't have a battery industry, and that's what will be great. And Peter Littlewood on the bottom right is the first director of the Faraday Institution. So I've had my concluding, so I think I can get it done, hopefully. So what does the future bring? One thing is certain about the future. It's uncertain, especially with Brexit. But I'm a natural optimist, and I think it's a particularly exciting and challenging time to be a scientist. Science is about innovation and discovery. So the really exciting thing about being a scientist is about discovery. And for me, it's discovering new materials, new phenomena, but the underpinning science is crucial. For those in this area, I'm hosting a discussion meeting at the Royal Society called Energy Materials for a Low Carbon Future this September, and that's on the Royal Society website. And I can't leave without mentioning the Christmas lecture. It was a real privilege and honour to be asked to do the Christmas lectures back in 2016. It was the 80th anniversary of the Christmas lectures, so I had the privilege of actually inviting lecturers past to attend, and I thought I'd show you briefly the intro. If you haven't seen the lectures, shame on you, but I forgive you. But, they're on the Royal Institution website and on YouTube, and this is the intro. Hopefully that'll make you go and watch it. So I love the Royal Institution. I grew up in Crouch End, overlooking Alexandra Palace, and I didn't realise that 1936 was the first televised Christmas lectures in 1936. I went as a school child, being a Londoner, went to lectures by George Porter, and then gave lectures as a PhD student because my PhD boss was there, Richard Catlow. And as I said, I could invite lecturers past. In the first one, despite my name, I am a devout humanist, and Richard Dawkins appeared to reprise one of his demos he did with a pendulum. In this case, you can see I added some spikes to that pendulum. And also, the Royal Institution going to be in the Guinness Book of World Records again. We actually built the largest battery made of lemons. We used 1,008 lemons, cut them in half to get 2016 lemon slices, so it was cutting-edge technology. And we broke the world record, so again, you can see a clip of that. Here, I have to acknowledge and thank the Lloyd Register Foundation for their support for the Christmas lectures and the support for the Royal Institution in general, Richard Clegg and Tim Slinsby. It was great meeting just before the lectures, and there's some of the photos and some of the Guardian pieces. But also, Richard may have forgotten this, but just before the lectures, he gave me and sent me by PDF clips of a newspaper. So Richard, I don't know if you remember, Richard, I remember this. So the first televised lectures back in 1936 was actually given by Professor Major G.I. Taylor, who was a professor of the Royal Society. And let me just read out a bit of this. The lecture was about ships. And right at the end, he has chosen for his subject ships. By doing, he has made a curious omission, for although the present is the 111th course of lectures, is the first on ships. In fact, I think it's the only one on ships. So anyway, that is the 80th anniversary lecture, was my one 80 years later. And I'm running out of time, so I'm going to end with a quote very quickly. Oh, some info. If you want some more information and some other 3D images, you can Google Saiful Bath. I promise you won't get a dodgy image. But if you want to, Royal Institution maybe go onto Twitter, so you can tweet photos of yourself, Saiful Chemistry and 3D Specs Chem, like these kids have done. I think they've formed a boy band now. And some other well-known people as well, the well-known chemist on the left. Lastly, I have to end with a quote. And to me, this quote is really for the youngsters in the audience, because you are the future generation, hopefully, of scientists. To me, it's a quote from an exhibition by one of my other scientific heroes, Charles Darwin. And the quote, to me, speaks to me about chemistry in general and modelling in particular. And the quote is from Marcel Proust. The quote is, "The real voyage of discovery consists not only in seeking new landscapes, but in having new eyes." On that note, thank you for your attention.
Thank you very much, Saiful. I think we've got 5 minutes or so for questions, but I just recollect I had the opportunity to go with Richard to see one of the Royal Institution lectures being filmed last year, and there's always a powerful visual image I take away, and you've given me loads more powerful images, but I just can't help noticing that actually Richard's a bit ahead of you, because look, you've got lithium-ion, written in Life Matters. So already we're on maybe. I'll never be able to look at Life Matters without thinking of lithium-ion again. So to that, we've got some roving mics. Does anybody have any questions? No question? Oh, one question there, sorry, in the pink top, just there.
Hi. Hello. Hi. My interest is in terms of sustainability and life cycle analysis. So the products you've spoken about here is about how we use the products in daily life or wherever it's going to be used. My question is, in terms of life cycle analysis, cradle to cradle, all those philosophies, when the minerals are coming from Northeast India, they're coming from Balochistan in Pakistan, lots of countries around the world. And then when I see, when I speak to my friends from these different countries as well, and they're telling me these minerals like the lithium and the bauxite and stuff, this is 5-6 years ago, and I was like, hold on a second, I thought it was clean green energy. It doesn't sound very clean to me. And they're describing it because a lot of them live in the pits now. When I ask these questions to the environmentalists or the green people here, and I'm a greenie myself, and they say, well, this is the better of the worst options. And I then show them the photographs of Balochistan and other places, and I say, is this still the better, worst option? It's not my backyard, but it's someone else's. So I just wanted to ask with regards to that, especially the two words you've got at the moment, which is bringing safety to life because life matters. Whose life matters exactly? Is it just the people who get the benefits of the products in the West, wherever it is, or is it the people who also are mining the products as well? Thank you.
Well, I think there's a lot of elements in there. I am just a humble scientist, so in terms of the socioeconomics of world capitalism, I can't comment on. But you're right, there are issues with sustainability and getting the minerals, and how the West relies on minerals and other resources, not just minerals, from the less developed world. I can't say I have a simple answer to that in terms of a different economic model, a more sustainable economic model that actually assists and helps to develop the less developed world. But yeah, I mean, it's a major issue. I mean, but I don't have a simple answer to it.
Thank you. We've got two more questions. There's one question at the front, and then lady just over there as well.
Thank you. It's actually just it's Ruth Bunbury from the Foundation, Lloyd Foundation. I think the question is a really good question that came just before, and you know, we as a foundation are very conscious of the challenges that are coming about. Where are people harmed, and in what industries are people harmed? And we, you know, at the last conference we put out what are the global safety challenges, and these sort of challenges about whole life cycle analysis. You know, what's happening in the supply chain. This is all part of the bigger question about life matters. But science has a part to play in solving those challenges too. And I wonder if Rebecca from Sheffield is in the room at all. Is she? Yeah. Hi. So you know, the foundation is also putting money into Rebecca. If you're waving your hand around there, we're supporting Rebecca, who is the highest finishing Royal Academy Fellow in her year, and she is looking into alternatives to the mining of these kind of minerals in her working on nanotechnology. So hopefully, you know, by the time Rebecca's got to it and expanded her work, that we'll have alternatives for these kind of mined minerals. So perhaps you guys should have a conversation afterwards.
Thank you. Thanks, Ruth. This lady there.
How long will we still have lithium batteries, and what will be the next battery material beyond lithium?
So there's a lot of research going beyond lithium. So if I call it below lithium, because if you look below lithium in the periodic table, it's sodium. And sodium is much more abundant. And so there are research, particularly for the renewables. I mentioned grid storage as one of the areas. So sodium-ion batteries, where scale is less important, rather than small size for your phone. Sodium-ion batteries are being looked at, so that's a big area of research. Trying to move away from carbon to lithium sulfur and other materials. I can't predict, you never know 10 years, I mean, who'd have predicted even 15 years ago how ubiquitous the mobile phone has become? So it's very hard to say what will be the next one, but I would say sodium ion is a big area, and the solid state that I mentioned, solid state batteries. So those two areas are the growth areas.
I think that's all we've got time for on questions, so thank you very much, Saiful.
Thank you. Thank you.